Hi learners, welcome back to DHILK. In the previous video we discussed why amines behave as bases and how the basicity of amines can be measured using Kb and pKb values. And we also discussed that larger the Kb value and smaller the pKb values indicate stronger basicity. Now in this session we are going to continue that discussion and understand an important question: why are alkyl amines generally more basic than ammonia? And how does the order of basicity change in aqueous medium? We will also discuss the role of the plus A effect, solvation, hydrogen bonding and steric hindrance in determining the basic strength of amines. So let us begin step by step. First, let us compare between alkylamines versus ammonia. So we know that amines behave as bases because the nitrogen atom contains a lone pair of electron that can accept a proton, right? This nitrogen atom has a lone pair of electron which can accept proton. In ammonia, the nitrogen atom has a lone pair, and similarly in alkyl amines, the nitrogen atom also contains a lone pair. Both ammonia and alkyl amines, I am taking a primary amine, both of these nitrogen atoms has lone pair of electrons. But the important difference is the presence of alkyl group in amines. In ammonia, there are no alkyl groups. All the three bonds are achieved by hydrogen atom. But in alkyl amines, there is one nitrogen carbon bond. One bond is an alkyl group. Another two bonds to in primary amine, another two bonds are to hydrogen atom. And in secondary amines, there will be two alkyl groups and one hydrogen bond. And in tertiary amines, there will be three alkyl groups and one nitrogen atom, right? So, and we know that alkyl groups show a inductive effect, positive inductive effect. That's also known as plus I effect. Means alkyl groups donate electron density towards the nitrogen atom. Alkyl groups have a plus I effect, means they can donate electron pairs towards the adjacent atom. So here it can donate electrons to nitrogen atom. Okay, so what will happen as a result of this? As the electron density of nitrogen atom increases, the lone pair becomes more available for donation to proton. So because of this, alkyl amines can accept protons more easily than ammonia. Therefore, alkyl amines are generally stronger bases than ammonia. So look at this here. This is an alkyl amine. So it can donate electrons more easily to the protons than ammonia, because in ammonia only the lone pairs are present. There is no inductive effect, right? But in alkyl amines, since there is an alkyl group, it will donate electrons and that has a plus I effect, and so it can further increase the electron density towards the nitrogen atom. So it is more prone towards the proton addition. Okay. Now let us understand another important point. When the amine accepts a proton, a substituted ammonium ion is formed. This is an amine. So when amine is mating to a proton, it produces a substituted ammonium ion, right? This positively charged ion becomes more stabilized because alkyl groups helps disperse the positive charge through the plus I effect. So alkyl groups not only increase the electron density of nitrogen atom before protonation, but they also stabilize the conjugate acid formed after protonation also. So at the same time, in ammonia, after protonation, it is producing ammonium ion. The produced ammonium ion does not have any stabilization due to the presence of alkyl group, right? So here the ion is more stabilized in alkyl amines, not in ammonia. So these are conjugate acids, right? So these conjugate acids produced after protonation is more stabilized in alkyl amines. So both these factors increase the basicity strength of alkyl amines. Okay. Now if we consider only the plus I effect in the gaseous phase, if we are considering only the plus I effect, then the order of basicity is in such a way that tertiary amines, then secondary amines, then primary amines, then ammonia. Okay, amines are always have higher basicity than ammonia. Now we can compare with these three compounds. In primary amines, there is only one alkyl group, but in secondary amine there are two alkyl groups. In tertiary amine there are three alkyl groups. So as the number of alkyl groups increases, the plus I effect is also increasing, right? There is a plus I effect from three alkyl groups, so it will increase the electron density on nitrogen atom, so that the basicity will also increase. Hence we can say the order of basicity in gaseous phase, it is tertiary amine, then secondary amine, then primary amine, then ammonia. Okay. However, experimentally in aqueous medium, this order is not always observed. This order is observed in gaseous phase, but in the aqueous medium, this order is not observed. So now let us move to the next part where we will understand what happens in water. In aqueous medium, there are three important effects. More than plus I effect, there are two important terms that we have to consider. One is plus I effect, that we already discussed the plus I effect in alkylamines, but there are two more terms that we have to consider. One is solvation, then second one is steric hindrance. So we can say solvation or hydrogen bonding. We know because of the presence of electronegativity difference between the nitrogen and hydrogen atom. So firstly, the plus I effect is still favors higher alkyl substitution because more alkyl groups pushes more electron density towards nitrogen. According to this factor alone, tertiary amines should be the strongest bases, right? Because in tertiary amines there are three alkyl groups, so it can donate electron density towards the nitrogen atom in three different ways. So electron density will increase and it should ease the protonation process. If you think only this effect, then tertiary will be the amines which has highest basicity. But now another important factor comes into play is solvation. When amines become protonated in water, the resulting ammonium ion interact with water molecules through hydrogen bonding. So look at this. This is a primary amine. So when it is dissolving in water molecule, there is a possibility of formation of hydrogen bonding with the water molecules. So better hydrogen bonding means better stabilization of the ion, and more stabilization means greater basicity. So in primary amines, there is 3 hydrogen atom, so better hydrogen bonding is possible. In secondary amine, there is only 2 hydrogen atom and it can form hydrogen bonding, while in tertiary amine there is only 1 hydrogen atom in the substituted ammonium ion. So once the hydrogen bonding becomes better hydrogen bonding means better stabilization of the ion, and more stabilization means greater basicity. So primary ammonium ions have 3 NH bonds, so they can form maximum hydrogen bondings with water molecules. Therefore, they are highly solvated and strongly stabilized. So primary amines are highly solvated and highly stabilized. In secondary ammonium ion have only 2 hydrogen bonds, so hydrogen bonding degree slightly. Tertiary ammonium have only 1 NH bond and bulky alkyl groups surrounding the nitrogen atom. There are 3 alkyl groups present and it is surrounding the nitrogen atom. So hydrogen bonding with water becomes very less effective in tertiary amines. This introduces another factor called steric hindrance. Due to the presence of the alkyl groups, we have to consider one more term, that is steric hindrance. Bulky alkyl groups block hydrogen bonding with water. So larger the alkyl groups means less solvation. So bulky alkyl groups around the nitrogen physically block water molecules. Okay, so this is preventing the water molecules getting solvated with the nitrogen atom. Bulky alkyl groups around nitrogen physically block water molecules from approaching the ion properly. As steric hindrance increases, solvation will decrease. So even the tertiary amines have a strong plus I effect, they are poorly solvated in water because of steric hindrance and reduced hydrogen bonding. So therefore in aqueous medium, the observed order of basicity becomes different from the gaseous phase order. Now let us understand the experimentally observed order in water. So for ethyl-substituted amine, the order is C2H5 twice NH, then C2H5 thrice N, then C2H5 NH2, then NH3, means secondary, tertiary, primary, then ammonia. In methyl-substituted amines, the order is CH3 twice NH, then CH3NH2, then CH3 thrice N, and then NH3, means secondary, then primary, then tertiary, then ammonia. Here it is 231. Here it is 213. Okay, just easily you can understand. 231. Here it is 213. Okay, so here what is happening? In the secondary amines are the strongest bases in both of this case. In ethyl-substituted amines and methyl-substituted amines, in both cases, secondary amines are the strongest bases. Why? Because secondary amines have a good balance between plus I effect and solvation, right? So they have enough alkyl groups to increase electron density, but they are still not too bulky to prevent hydrogen bonding completely. tertiary amines have a stronger plus I effect, but steric hindrance reduces solvation significantly. Therefore, their basicity decreases compared to secondary amines. Now let us look at the methyl-substituted amines. Here what is happening? In the secondary amines are the strongest bases, but here primary amines become more basic than tertiary amines because methyl groups are smaller than ethyl groups. So smaller alkyl groups create less steric hindrance, allowing better hydrogen bonding and solvation. So the important conclusion is that the basicity of amines in aqueous medium depend on the combined effect of plus I effect, solvation and steric hindrances. Okay. So in ethyl-substituted amines it will follow this order, and methyl-substituted amines it is following the order. So if the alkyl groups are small, steric hindrance is less and solvation become more effective. But when alkyl groups become larger, steric hindrance increases and reduces hydrogen bonding with water. That is why the order of basicity changes depending on the nature and the size of the alkyl group. So learners, this is a complete explanation for the basicity order of alkyl amines in aqueous medium. So finally we can say when the alkyl group is small, there is no steric hindrance to hydrogen bonding. When the alkyl group is larger, steric hindrance to hydrogen bonding sets in, and therefore changing the nature of the alkyl group. For example, here CH3 to C2H5 changes the basicity order. So basicity in aqueous state depends upon three factors: plus A effect, solvation effect and steric hindrance. So in the next session, we will discuss the comparison between aryl amines, ammonia and aliphatic amines, and we will understand why aromatic amines like aniline are less basic, along with the role of resonance and substituent effects in determining their basicity. So keep learning with DHILK, and I will see you in the next video. Bye.